All right, Chapter 2. Introduction to, oops, this is in Chapter 2. Let's get to Chapter 2 here. Basic tools of analytical chemistry. All right. In this chapter, we're going to learn about the different measurements, different units that we use. We're going to talk about significant figures, concentrations, reactions, balanced reactions, moles. Most of this will be review, but some of the problems will be a little more in depth than what we were used to. Okay? Very good. So, measurements in analytical chemistry. All right? So, units that we use for measurement. Hopefully you've heard of the SI unit, which stands for Standard International Units, or the International Standard Units. These, when I was a student, I kind of thought, okay, these are the International Standard Units, these are the ones that I have to use. But it doesn't actually turn out that way. The internships and experiences that I've had where I've gone and worked with companies, they've always used different units, just whatever units culturally they have become accustomed to. So it's nice to kind of know the international standard units. They're always there to be, it's always easy to look them up and find out what they are. But more than anything, you have to be ready, flexible, to work with whatever units the lab that you're interacting with uses. Okay? Now, this has caused significant issues in the past in terms of labs working together and thinking they're using the other lab's units. So it's never inappropriate to make sure you have a conversation about the units that you're going to be used. Okay? So we don't need to spend any of our brain power trying to memorize conversion factors, right? I mean, there's some conversion factors that are nice to know and that we know. What's a conversion factor? Good question. Conversion factor. So a conversion factor, there can be anything from 12 grams of carbon to 1 mole of carbon, right? So essentially we're saying these two are the same as each other, all right? Or you could have a 1,000 millimeters. Whoops, there's supposed to be a little m there. For every 1 meter, right? That is another conversion factor. Conversion factors can always go upside down. 1 meter is 1,000 millimeters, for example, right? All of these are conversion factors. In the more classical sense, especially because we were talking about different units, you can ask, for example, how many pounds are in a kilogram, right? Let's see. So that example is 2.205 pounds is equivalent to 1 kilogram. That's another example of a conversion factor, right? And I'm expecting, but I'm willing and likely going to help us remember how to use unit analysis. For example, if I had a question like, how many moles of ammonium carbonate are in 6 grams of ammonium carbonate? Okay, do you remember how to do this one?
Not quite. So you put the moles of ammonium carbonate to the right of the equal sign?
That's right. We always put the units that we're after over here. So that's moles of. Now, do you remember the chemical formula for ammonium carbonate?
No, I'd have to look it up.
Well, the ammonium ion, NH4, and the carbonate ion, CO3, this is a positive charge, 2 minus. Does that help?
Yeah, so they come together and neutralize, so it's NH4 2 CO3.
Very good. So we're looking for moles of NH4 2 CO3, ammonium carbonate, right? And we start off with 6 grams of NH4 2 CO3. Okay, so we go from grams of NH4 to CO3 to moles of NH4 CO3, ammonium carbonate. Okay, so this is a conversion factor that we used here. Do you remember this?
Is that just the molar mass?
That's right, the molar mass of ammonium carbonate. Do you remember what that is?
I'm not sure.
I think it's 96, but we can ask our phone just as easy. What's the molar mass? What's the molar mass of ammonium carbonate?
The molar mass of ammonium carbonate is 96.09 grams per mole.
So 96.09 grams, so 6 divided by our 96 would tell us how many moles we have in 6 grams of ammonium carbonate. Okay, so using a conversion factor, and this, what we call unit analysis, is going to be very important to make sure we have the blueprint convincing ourselves. We can see that grams of ammonium carbonate there cancel out, and we're left in moles, right? And we know that these values are correct. So it's a blueprint to convince ourselves and others that we have the right answer. Okay, so it's a tool that we want to remind ourselves of and continue to use moving forward. All right, so here we are. Whoops. Okay, so our units. Again, like I mentioned, lots of units that we probably wouldn't even imagine people would use, but that's all right. We just have to be familiar with them, and you can get up to speed really quickly when you come into a new lab or a new company. Prefixes. Our prefixes are what we want to use. We never want to be presenting numbers outside the realm of thousands, usually, right? Or smaller than 0.001, for example. Most of the prefixes that we'll have to use are between nano and mega, all right? So megabyte, megameter, millimeter, centimeter, kilometer. You hardly ever hear deca or deca or hecta being used. But you'll hear a lot of micro, some nano, a lot of milli, and kilo, and a little bit of mega. All right, so I'll let you go back to those and remind yourself of what that all means if you've forgotten. Okay, so when we make a measurement, it provides us information about the magnitude, the amount of the material that we're measuring, amount of measurement that it is that we're measuring, whatever it is, and it also gives us information about the uncertainty. Now you guys have probably seen this before, where you put a mass or something on the scale, and you see within a very small time frame some changes, some shifts like this. Now sometimes this is indicative of a problem with the mass, or the scale, but not always, right? Sometimes there is shifting occurring, and we have to kind of know how to deal with that sort of thing. This is usually if it's a balance, it's the problem with the balance, but oftentimes the measurements, changes in our actual measurements aren't cut and dry like on a balance, right? We're reading an electrical signal, which can have some background easily, or a more sensitive electrical signal, I should say. So here, probably the best thing we could do is report our 5.730 with a plus or minus 0.001, indicating the magnitude, 5.730, and what we call the absolute uncertainty. All right, it's plus or minus 0.001 grams. The absolute uncertainty is always with the last number. Do you remember what the last number is in significant figures?
Oh, it's an estimate.
That's right. When we report that value, it's considered an estimate. So we can put an absolute uncertainty on that estimate whenever we collect or recognize the appropriate scenario. All right, significant figures. Here's a measurement, 0.0990 grams. The 0 green is significant because it's placed there as an indication that that's our last significant figure, or that's our estimate. The zeros in front here are not significant. It looks like this tool had the ability to measure stuff there, so if there was something there to measure, it could measure it, but those values are not significant. There are other rules for significant figures. Hopefully you can catch yourself up on those. I think this is something that you should have remembered how to do, but you might have forgotten, and that's okay. I'll provide some links to some videos that talk about significant figures, and you can catch yourself up, and then be ready to answer these types of questions. Okay? Significant figures in calculations is also important. Remember, when we add our significant figures together, we have to add or subtract, we have to line things up, and where the last significant digit ends, right? So this number ends significant digits in its hundredths place. So our answer has to end in the hundredths place. All right. When you're working with scientific notation, you want to first convert each measurement to a common exponent, right? Then you do the same thing, add them up, and again we have to end where our significant digits end. So here we're going to end with that's where our last significant digit can be used. So the answer will be 6.21 times 10 to the 7th. In multiplication and division, right, that's the easy one. You just count the significant digits in the different numbers that you're multiplying or dividing. This one has 3, this one has 4, this one has 5, and then we use the one that has the fewest number of significant digits. Now, I rarely find myself in a scenario where I need to be terribly careful about the number of significant digits. But I think what's more important is understanding. I mean, you never want to embarrass yourself by reporting too many significant digits. But what you need to do is make sure that in any analytical method, if one small step in the method limits your significant digits down to 1 or 2 significant digits, then that can really destroy the whole method. So you have to make sure that you don't allow that to happen, or recognize steps in an analytical method that will limit your precision because of that, right? All right. Let's see. Okay, so they provide some what they consider helpful hints for identifying significant figures. The very important thing about analytical chemistry is providing you a source, a resource to turn to when you have an analytical question. All right. Now, unfortunately, this is an e-textbook that unless you print it out, you're not going to be able to take it with you. I still have my analytical chemistry book from when I was an undergrad, and I use it as a resource. And I would do the same if I were you. So if you are going to be moving on in chemistry, I have a feeling that this link will be there, but probably more likely a different analytical chemistry text will be available as well. And turning to those texts and knowing where to look to answer such questions is more important to me than kind of memorizing these and rarely ever having to utilize something like this. Okay? Very good. So let's move on to 2.2, concentrations. Concentration. Concentration relates solute to solution. Now, do you remember what solute means?
Solute is the stuff that's dissolved in the water.
Okay, dissolved in the solvent. And yeah, usually we use water, but we don't want to ever limit our thinking that way necessarily, right? It could be an organic solvent. It could be nitrogen gas, an example of air, right? So solute is what's dissolved in the solvent. And what happens when you put solute in a solvent? What's the result?
You mean solution?
That's right. You get a solution. All right. So there are lots of ways to express concentration. And, it would be a wonderful world if, in my opinion, if everybody used molarity, right? Because then we could relate our concentrations to our chemical reactions, which are in mole-to-mole ratio more easily. However, there are lots of different ways of expressing concentration, and lots of different labs used lots of different ways of expressing concentration. So we have to be flexible again and be ready to adjust our thinking depending on where we end up. All right, so as a formality, we're going to introduce formality, but we're not going to ever use formality. It is well, kind of a archaic, but still important in some realms, maybe. So essentially what formality refers to, it's the same as, can be the same as molarity for something that doesn't disappear when you put it into solution, I guess you could say. So let's look at an example here. So for 1 molar sodium chloride, all right, if I have 1 molar sodium chloride, what does that mean to you, Fred?
You have 1 mole of sodium chloride per liter of solution.
Very good. 1 mole of sodium chloride per liter of solution. All right, 1 mole of NaCl. How did I make this solution?
You took 1 mole of sodium chloride. Is that 58 grams?
58 grams. Good.
1 mole of sodium chloride, and you dissolved it in 1 liter of water?
That's right. That's exactly what we did. Now, what happens when you put the sodium chloride in water, though?
It dissolves.
All right, dissolves. What happens when you put an ionic compound into water? It's a little bit different than dissolving. Do you remember?
No, I guess I don't.
Well, it dissociates. Do you remember that?
Oh, yeah. It dissociates.
Into the sodium ions and chloride ions, right?
Yeah.
So if somebody said, I have a solution that's 1 molar sodium chloride, somebody else might say, you don't have any sodium chloride in that solution. You only have 1 molar of sodium ions and 1 molar of chloride ions. No sodium chloride. And so that's true. And to kind of have an upfront concentration when necessary, we use formal to say, I have a solution that's 1 formal sodium chloride, or the formality of the solution is sodium chloride. That means that I'm speaking appropriately and recognizing that I don't have any sodium chloride. It's all sodium ions and chloride ions, but I'm emphasizing that fact by calling it a 1 formal solution. Okay. The other unit of concentration here that is kind of similar in terms of its kind of expression, not as archaic, still kind of important, but kind of argued about it sometimes, is normality. Now, normality is referring to the concentration of so an example for normality is if I have a solution of, let's say, H2SO4. Now, do you remember what kind of compound that is?
Is that an acid?
Yes, that's an acid. Very good. So if I say I have a solution of 1 molar H2SO4, that's expressing, again, that I put in 1 mole of H2SO4 into a liter of solution, diluted it with water. But if I'm talking about this in terms of its acid component, I need to recognize that it's not 2 molar acid. It's not 1 molar acid. It's actually 2 molar acid. And so we use the term normal when we want to talk about the amount of the acidic component or the amount of the active component that we're using that solution for. So we say this is 2 normal H2SO4 because H2SO4, when it dissociates, it releases 2 hydrogen ions. Okay? So that results in twice as much acid as the H2SO4 that I put in there. Does that make sense?
Yeah, I guess.
Again, you won't find yourself needing to understand this or use it too frequently, but they are nuances in analytical chemistry which we want to be aware of. Okay, good. Okay, so weight percent, or molality. Well, I don't think we'll ever talk about molality again after we introduce it. We've introduced it in Chem 106 to you guys as well. Do you remember what molality is?
Moles of solute, kilograms of solvent. It says right there.
Good, that's good. I'll let you leave that to you to think about later if you ever need to. You know where to look for it. Weight percent, grams of solute for every 100 grams of solution. This one is used more frequently in industry, so you want to become familiar with that. All right? So maybe I can envision some quiz questions where we convert between molarity to weight percent. Now, volume percent, this is also relatively important because when you're making a solution of between two liquids, you're going to usually use volume percent as an expression of concentration. Isopropyl alcohol, do you know what that is?
Is that the stuff in the medicine cabinet?
Yeah, that's right. Alcohol that you use in your medicine cabinet, it comes in either 30, 70, or 90% isopropyl alcohol. And that's relative to the overall concentration, right? Okay, very good. And then we have something that's kind of important also in terms of analytical chemistry, and that's parts per million. Parts per billion are self-explanatory once you understand parts per million. Let's give a little bit of an explanation as far as what parts per million means. I mean, I think the phrase parts per million is pretty self-explanatory. 10 parts per million is, you've got a million parts and 10 of them are different, right? 10 out of the million have are your analyte of interest, right? But how do we kind of remember that, and how do we use parts per million? Okay, so there's two things that you can do to remember parts per million. One is just to remember, which is milligrams of solute for every 1 liter of solution. And I think most people generally do this. They just memorize that as parts per million.
That's parts per million?
That's right. And it can also be expressed as micrograms of solute for every milliliter of solution. You can see how those two are equal, hopefully.
Yeah, I see that.
Now, let me try to explain to you why parts per million is this ratio. First of all, it's taking into account that generally these are aqueous solutions. These are generally aqueous solutions. Therefore, the density of the solutions, they're not just aqueous, they're aqueous and they're relatively low concentration. That means the density of the solutions is always going to be what?
The density of dilute solutions, you mean like water?
That's right. It's essentially very close to water, or 1 gram per milliliter. So, that being the case, if I took a milligram of water, or let's say I want to say 10 milligrams to make this 10 parts per million. Okay, if I took 10 milligrams of water and had 1 liter of solution. Okay, we don't want water. It's 10 milligrams of analyte, whatever it is. We'll just call it X, for 1 liter of solution. 10 milligrams of X for every liter of solution. That's 10 milligrams of X for every 1,000 milliliters of solution. Is that the same?
Yeah, because 1 liter is 1,000 milliliters.
Very good. And if I said 10 milligrams of X is 1,000 grams of solution, is that okay?
1,000 milliliters is the same as 1,000 grams?
Yeah, is that okay? Are you comfortable with that?
How did you know that?
Well, remember we talked about the density of water. The density of water is 1 gram per milliliter. And the density of solutions that are very dilute are very similar to that of water, right?
Okay, yeah. So 10 milligrams of X for every 1,000 grams of solution.
Very good. Now, if I take this 1,000 grams and convert it to milligrams, I get 1,000,000 milligrams. So 10 milligrams of X for every 1,000,000 milligrams of my solution, right? And then that's 10 parts per million. Okay? Very good. So, parts per million is micrograms per milliliter or milligrams per liter. And then parts per billion are just, 1/1000th, the concentration of that. Okay, very good. So we talked about molarity, formality, normality. We briefly touched on molality, weight percent, parts per million. Okay, converting between these concentrations. Oftentimes, if you're going to do the conversion factors, you'll need to have the density, especially if you're going from molarity to molality. The density is also important when you're trying to find out grams of material based on a given volume. Okay, so you can never forget that your solutions aren't necessarily 1 gram per milliliter. You always have to kind of take into account the density. All right, very good. Now, P functions. P functions. Do you guys remember what pH is?
pH, that tells you the acidity of something.
Yes, it tells us the acidity of something, but it also expresses, it's, so if I have a high pH, what does that mean in terms of, is that acidic solution or a basic solution?
High pH? I think that means it's really, I can't remember.
High pH is basic solution. Low pH is acidic solution, okay? Now that's something that, we'll generally remember if you ever interact with acids, but the P function is a mathematical function that is just the negative log of whatever it is you're talking about. So if I have the P of X, it's the negative log of X. pH, therefore, is the negative log of the hydrogen ion concentration, and the hydrogen ion concentration is in units of molarity. All right? So, for example, the pH of a solution that has a 0.1 molar H plus ion is 1. All right? Now, you can put that into your calculator and always kind of remember that the negative log, right? I want to make sure you know how to do that. Negative log of your hydrogen ion concentration will equal 1. pH, when it's a nice easy number like 1, 2, 3, 4, 5, whatever, it is essentially telling you that how many times you move the decimal place to the left on the number 1. Okay, so let's see. We have some examples here where we not just look at the pH, but we can look at PNA, P sodium ion, for example, right? Essentially going to take the negative log of the molarity of the sodium ion. Now what that does is it allows us to relate the concentration of our analyte, whether it's hydrogen ion or sodium ion or whatever it is, over a larger range, right? Because you can't express concentration in terms of hydrogen ion concentration very well between 0.00001 molar up to 1 molar on a linear range, right? However, it can be necessary to talk about hydrogen ion concentrations at these different pHs. It's very reasonable to go from pH 6 to pH 3, and the range there is very far, right? Okay, very good. Well, we have some problems there that I would become familiar with if I were you, to make sure that you can remember how to identify the pH given the hydrogen ion concentration, and to find we also want to make sure we're familiar with how to find the parts per million of a solution if we are given molarity. Also want to make sure we know how to find the weight percent. Weight percent, which is right here, grams of solute for every 100 grams of solution. There we go, weight percent. This one right up here. Okay. Very good.